Hello everybody. In this video we're going to start a new topic, which is the gas absorption and stripping. This is one of the famous applications in industry, and this is something that we are going to cover in the software, the Aspen Plus software. But I preferred first to go through the concepts of the absorption and stripping and do a quick review of these concepts so that we're on the same page, and if anyone is missing some piece of information, he kind of reviews it quickly and refreshes his information or her information. Um, so I'm going to start first by the definition of absorption. So absorption is an operation in which we use a solvent to dissolve one component in a gas stream. So let's say we have um, a mixture of gases, and there is one component that is not of interest, and I want to get rid of this component, so I use a solvent to dissolve it selectively without dissolving the rest of the components. And this is used in many applications industrially, and one of the most famous applications is the removal of acid gases from natural gas. So acid gases are like the gases that form acids when they react with water, like carbon dioxide, carbon monoxide, sulfur oxides, and hydrogen sulfide. And these make a lot of problems when we go through the natural gas purification and the processing of natural gas. So it's important to get rid of these components, and the one of the most famous methods is absorption. The other is kind of environmental related thing. So if you have a gas or air that you want to go move to the environment, and it has a component that is pollutant, you have to make sure that the concentration of this pollutant does not exceed the regulations. And one method that you can purify this air is by absorption, like the absorption of ammonia from air. So there are many other applications of absorption. But before we go into the topic of absorption in deep, we have to understand the uh, the limit of absorption, and what we call the equilibrium solubility of gases and liquids. To understand this concept, let's assume that we have a closed container that has a gas and liquid phases. And this gas has a mixture of components, and only one of them can dissolve in the liquid phase. Um, and you're keeping them in this closed container for a very long time. You did all what you can do to make sure that there are no mass transfer limitations. You shake it well, you do everything, and you leave it for a very long time, for like 1 or 2 weeks, and then you check the mole fraction or the composition of this component that dissolves in the liquid in both the gas and the liquid phases. So the mole fraction in the liquid phase is going to be y, and in the gas phase is going to be x. And at some point, or it's going to start by diffusion or mass transfer from the gas phase into the liquid phase, and it's going to go on and on and on, and until it reaches a point where the mass transfer stops. And it stops because the composition in the gas phase is in equilibrium with the composition of in the liquid phase. And this is what we mean by equilibrium, which is the compositions that do not have any further mass transfer going between the two phases when they take place. Um, the liquid in this case is called a solvent, and this species that is dissolving in the liquid phase is called the solute, and the process is called absorption. The absorption process and the maximum solubility is function of many things. It's function of the type of solute, the solvent. It's function of the temperature. It's a function of different things, and that's why we see these charts, which kind of summarizes many informations in one place. So this is the solubility or equilibrium solubility of different components or different gases in water. And here in the y-axis we see the partial pressure of the solute, which is kind of representation of the composition or the concentration in the gas phase. So sometimes it's expressed by partial pressure, sometimes it's expressed by mole fractions, which is this y. And here we have the mole fraction of the solute in the liquid, which is x. And we have many graphs here. We have A, B, C, and I assume this is E. So it's kind of important to like spend some time here to understand or get some information from this chart. So the first thing that we will see here, if we compare chart number or curve number B to curve number A, I mean A and C, the three are at the same temperature, but the curve takes different shapes because of the different solute that is dissolving in water. So despite having the tests done, or the curve done in the same temperature, which is 10 degrees Celsius here, here, and here, but the HCl behaves differently from ammonia, from the SO2. So which of them have the highest solubility? So if we think of solubility, it's the gas will be more soluble if the X is very high and Y is very low. So it can dissolve a lot of the solute. So X is a big number, and it's going to be in equilibrium with very small amount of the solute in the gas phase. So Y is small. So it's going to be a good solvent if the curve is low. So you have very high values of X corresponding to very low values of Y. So for instance, here for HCl, the 0.15 mole fraction of HCl is in equilibrium with, it's less than 10 millimeter mercury of HCl, while the same amount or the same mole fraction is going to be in equilibrium with almost 80 in case of ammonia, and the SO2 is not there, it's far away from this curve. So the HCl is highly soluble in water, ammonia is less soluble, and SO2 is very springly soluble in water. So this is one thing that we can learn from this curve. The second is comparing these two charts, or these two curves, the E and A. So both are the same solute, but this is at 30 degrees and this is at 10 degrees. And applying the same concept, it's clear that the solubility at 10 degrees Celsius is higher than the solubility in at 30 degrees Celsius. So it's kind of a rule that if you increase the temperature, the solubility will decrease, and this is something that has many impacts on our life. So one of them is the what we call the thermal pollution. So this is one sort of pollution where the temperature of the water bodies increases, and if it increases, the solubility of oxygen in water decreases, so the oxygen depletes from the water. And the fish and the marine creatures die due to this phenomena because of the lack of oxygen in the water, or the decrease in the amount of oxygen in water. So to kind of go more with the equilibrium solubility of gases, there are relations that were developed to kind of describe this solubility or this equilibrium relation mathematically. So one of them is Raoult's law. We can use it in case of ideal solutions. And Raoult's law says that the partial pressure in the gas phase is going to be equal to the vapor pressure multiplied by the mole fraction in the liquid phase. So this is one relation that can be used in ideal solutions. For non-ideal solutions, we can use the Henry's law, which is Y equals M multiplied by X. It's usually H, but in case of absorption, they like to put it as M, but it's the same thing. But Henry's law is used in very low solute concentrations in the liquid phase. So if you take a look at these two equations, we can see that they are kind of straight line equations. And this is what we can see here. For the small mole fraction in the liquid phase, this part is straight line, this is straight line, this is almost straight line, and this is straight line. So we can use the straight line equations in case of very low solubility in the liquid phase. But as the the mole fraction in the liquid phase, but as the mole fraction increases, we see this deviation from the straight line here. So it's not straight line anymore. So that's why in some cases we use the experimental data. So we do experimental tests and we get the results as tables of Y versus X, and we can use these tabulated data as representation of the equilibrium relation between the solute concentration in the liquid and in the gas phases. So now, based on this, how we can choose a good absorbent. So a good absorbent or solvent must have the very first a property that's important and which will dictate if we can use this solvent or not is the solubility of the solute in this solvent. Because as we use a highly soluble or a solvent that has high solubility of the solute in it, we will use smaller amount of the solvent, and this is going to be more economic and more easier to work with. The second is the low volatility, because we will see in few slides that we will do the stripping, and the stripping will kind of include high temperature. So we don't like to this stripping to take place in the absorption, or we don't. I'm sorry, we don't want the solvent to evaporate while doing the absorption. So we don't need losses in it, and again, to make the stripping process more easy and more convenient. It's better to be non-corrosive material so that it does not make us use high cost or high price material of construction. The solvent shouldn't be expensive, and shouldn't be viscous. The viscosity is important because it makes the pumping of the fluid less costly. And finally, to be safe to work with, so it shouldn't be explosive, flammable, toxic, so that it's safe to work with and doesn't make hazards to the people working with the absorption process. Now let's see what kind of equipment that we use to do the absorption in. So the absorption process takes place in columns like the columns we use for distillation. One of them is the packed column, and we see here the packed column contains packing, which is just something that's put inside. It has many shapes and many types, and its function is to create an area for the gas and liquid to meet and let the mass transfer take place inside. The gas enters the column from the bottom, and this is going to be the same for tray and packed column. It's not going to be different, and gets out from the top as a clean gas, and the liquid solvent enters from the top, and it goes down meeting the gas that's coming from bottom to up, and takes the solute and comes out as a rich solvent which has the solute. The other is the tray column, which is almost the same as the distillation column, the tray distillation columns. Again, the feed gas is fed from the bottom, the fresh solvent is fed from the top, and they meet while the solvent is going down and gas going up. The scrubbed gas comes from the top, and the rich solvent comes from the bottom. It's important to notice here that we do not have here a reboiler, and we do not have here a condenser, and this is one important difference between the absorption and distillation, which is that we do not need the condenser and reboilers here. We'll see that we need them in the stripping column, but in the absorption column we do not use these. And now one thing that is important, and we kind of spend long time to do, is to calculate the amount of or number of stages that we need to perform the purification. So we need that we know that the amount of or the flow rate of the feed, and the composition of it, and the mole fraction of the solute in it, and the required purity that we need from the gas after absorption. And we know the composition of the solvent, and we know the amount of the solvent that's coming out, and from mass balance we can tell how much solute will be in there. So we need to know how many stages I need so that I can achieve what I have just said. So the way we do this is by doing tray-to-tray calculations, where we do mass balance, energy balance, and the equilibrium calculations on each stage. And this stage will give information to the next, and so on until we reach the bottom stage, and then we know that this is the amount of or number of stages that we need to achieve this absorption. But as we mentioned before, this is very close to what we mentioned in distillation before. It's very tedious, time-consuming process, and it includes a lot of iterations, and it's not easy. So there is another way that we mentioned before, or used before in distillation, which we can use here now, which is doing the graphical solution. So this is gonna be kind of very similar to what we did in distillation. So the next slides will not be doing something new. It's gonna be more like what we did in distillation, but with the system of absorption. So we mentioned before the equilibrium relation um, here, and we said that we can use the equations or use tabulated data. But for the so this is for the equilibrium curve, and now for the operating line, we have to do kind of derive the equations. So for the equations that we're going to use are going to be overall and component material balance over the whole column. And as I mentioned before, from this we can know the XA, which is the mole fraction of the rich solvent, and we can know the amount of solvent that we need. This is something that we will come to in few slides, which is the amount of solvent. But we can know from the material balance the information from the inlet and outlet streams to the column. The operating line should include what we have inside, so we can do mass balance on this loop, and it's gonna end up like this. We're gonna put it as y as a function of x, so we can fit it with the same equilibrium curve, which is y as a function of x as well. So from this equation, it's clear that it is y equals something multiplied by x plus something. So it's a straight line equation, or it looks like a straight line equation. But if we plot this line, it's gonna be a curve. It's not a straight line. And the reason it's a curve is because the L and V are not constants. If we take a look here, if we have 100 moles of the solvent going in, they're gonna go from the top to down, and as they go down, they are gaining more moles by dissolving the solute from the solvent, from the gas. So the number of moles here, if they are 100, this is gonna be 105, and if this is 100, this is gonna be 95. So 5 moles of here are lost to here. So that's why the L and V are not constant throughout throughout the length of the column. And as we mentioned before, when we do graphical solution, we prefer to use straight lines because the curves are not easy to work with. You have to put many points, and these points must be like 5 or 6 points so that they can describe the operating line precisely. So we usually like to use straight lines because we just need 2 points and we are done. So there's a trick then that we can use that we can let us or enable us to replace this curve with a straight line. And this trick is using what we call the solvent or solute-free basis. To understand what I mean, let's take a look at this figure. We have here the liquid phase, which is going from top to down, and the gas phase, which is going from down to up. And as we see, the liquid phase has amount of solute which is not very much, it's just traces of the solute, and the gas phase has a lot of solute in it. And what's gonna happen is that the solute is gonna diffuse from the gas phase until it goes into the liquid phase, and finally the product is gonna be a gas phase with a small amount of solute and liquid phase with a large amount of solute. So this is the idea in a nutshell. What we see here is that the number of moles here is different from the number of moles here, and here is different from here, which is what we just mentioned before. But we have to keep in mind that the change that happens is only in the number of moles of solute in the liquid and the gas phase. It's not in the solvent itself or in the gas phase itself. So the number of moles of the solute or the solvent without the solute is constant, and the number of moles of the gas phase without the solute is constant. So this is what we mean. Mean by the solute-free basis. That if I have 100 moles of the solvent going in and they come out as 105, they are actually 100 as they were in the beginning, plus the 5 moles that they gained from the gas phase. And the same here. If this is 100. It's actually 95 plus 5, so it's losing 5 and the rest is 95, which were the 95 that I started with from the very beginning. So if we can use the solute-free basis for the liquid phase and the gas phase, the L over V now is going to be a straight line. So this is the idea. So we need to kind of look at it from a mathematical point of view so that we can see how we can tweak the equations so that they can fit with what we are just mentioned. Now for the flow rates of the gas and the liquid, we are going to define the L dash, which is the solvent with the solute-free basis. So this is going to be, if we have like 10% of the solute in the liquid phase, then the solvent itself is going to be 90%, which is 1 minus X multiplied by L. And the same for the V dash is going to be V multiplied by 1 minus Y. So this is easy. There is nothing difficult in it. But we need to like take a look back at these equations. We used V and multiplied it by the mole fractions, and this is the total flow rate of the gas phase, and this is the mole fraction, which is the number of moles of solute divided by the total number of moles. So when we multiply these two together, it gives us the number of moles of the solute. And if we do the same here, this is not going to work because I cannot multiply this by this because the units are not going to be consistent. So we need to find mole or something that can replace the mole fractions X and Y that will fit with the L dash and V dash. And for this, we use the solute-free mole fraction, or it's going to be the mole ratio, which is the number of moles of solute multiplied by the number of moles of solvent. So when you multiply this X by this L dash, it's going to give us the number of moles of solute. And this is calculated from the mole fraction by this equation. It's X divided by 1 minus X, and the same for Y, it's Y divided by 1 minus Y. We put the mole ratios as uppercase letters to differentiate between them and the mole fractions. And now when we multiply L dash by X, the uppercase X, and V dash by the uppercase Y, it's going to give us the number of moles of solute. Some people kind of get confused from this equation, but it's kind of simple. We know that the X is the number of moles of solute divided by the solvent plus solute, and 1 minus X is the rest, which is the solvent divided by the solvent by the solute. So if you divide this by this, the denominators will cancel out, and we'll end up with number of moles of solute divided by the number of moles of solvent. So it's kind of easy, and you can do the opposite to get the mole fraction from the mole ratio. You can try this by yourself. It's going to be the same thing. Anyways, so now when we do the graphical representation, the equation is going to be like this. It's going to be L dash divided by V dash, which is constant now, so it's a constant slope line. It's going to be straight line. So the operating line is going to take this shape, and the slope is L dash over V dash. And it's always above the equilibrium curve. And now to calculate the number of stages, all what we need to do is to do it the same way we did in the McCabe-Thiele diagram before, is to go down, left, down, left, down, left, and in this case we have 3 stages. One more thing that we need to mention is how we can decide how much solvent we're going to use, and this is one important thing. So from the equation and from the slope, we can tell that if we have a large amount of solvent, like in this case, the slope is going to be very large. If we decrease the amount of solvent, the slope is going to decrease a little bit, and as we decrease it, it's going to be smaller, and the operating line is approaching the equilibrium curve, which means that I need more number of stages. And if we continue to decrease the amount of solvent, we will end up with something like this, which is a pinch point, and at this pinch point the driving force is 0 because the operating and equilibrium line intersect, and this means that I need infinite number of stages here. So the solvent flow rate here is what we call the minimum solvent flow rate. So we usually use 25% more than the minimum, so that we can get reasonable amount of stages or number of stages for the absorption process. And now let's move to the next point, which is the stripping column. So what we mentioned, or we were just talking about this column, I forgot to mention that, this is kind of intuitive thing, that the absorption column should operate at low temperature so that we have high solubility. So this is not surprising, and it should operate at high pressure, and this high pressure increases the driving force, so it increases the partial pressure of the solute in the gas phase, so it increases the flow rate, or the mass transfer rate, so it makes the absorption process more quicker than it would be at low pressures. And this is something that we will test in the software when we do the simulation. Um, but here we have the rich solvent. I cannot get rid of this solvent. I need to regenerate this solvent and get rid of the solute so that I can reuse it, because it's something that I have put a lot of money in, so I cannot just get rid of it directly. So what we do is we take this solvent to what we call the stripping column, and this stripping column, the function of this column is to get rid of the solute and regenerate the solvent. So what it does, it's kind of like the distillation column. And as you remember, we mentioned that the bottom part of the distillation column is called the stripping section because it does exactly what we see here. The feed enters from the very top and it goes down, and some of it are evaporated using the reboiler, and they evaporate and go up, and then they meet the solvent that's going from up to down. And by doing this, we have the vapor which is rich in the solute. We have here partial condenser, and here we must have a partial condenser because we remove the gases and we recycle all the solvent back. And finally, we end up with the what we call the lean solvent. The lean solvent, this process takes place at the opposite conditions. Here, high pressure and low temperature. Here, low pressure and high temperature. To do the opposite, reduce the solubility and increase the driving force on the opposite side. And this solvent is reused. The temperature of this stream is high and the temperature of this stream is very low, and this is going to go to a high temperature column, this is going to go to low temperature column. So we use this heat exchanger to use the heat of, or cool this stream by this stream and heat this stream by this stream, so that we make use of the energy. It's very common to have another cooler here so that we can cool it more and until it reaches the desired temperature of the absorption process. So stripping column is kind of the twin of the absorption column. They usually go together. Um, when we do the graphical representation of the operating line for the stripping column, it's kind of like what we mentioned before. I'm not going to go through the equations because they're going to be the same thing. But the point here is that the operating line is below the the operating curve, or the equilibrium curve. The equilibrium curve is higher than it used to be before, and the operating line is lower. And the slope is L dash over V dash. And the V dash, by the way, is the vapor that's coming from here. And we can control the amount of vapor by what we call the boil-up ratio. So the amount of heat we give to the reboiler dictates the amount of vapor that's going up to the column. So as we increase the boil-up ratio, the V increases, the vapor flow rate increases. And as we decrease the boil-up ratio, the vapor flow rate decreases. So we can easily control it with the duty of the reboiler. And we can calculate the number of stages the same way as we did before. And we can have fractions because they are theoretical stages. One last thing is how we can decide the amount of vapor that we're going to use, or the boil-up ratio that we're going to use. So as we mentioned before, this is the slope, and here the parameter that we are changing is the vapor. It's not the liquid anymore. So this is the vapor flow rate. So if we decrease the vapor flow rate, the slope is gonna be higher. So it's getting closer to the equilibrium curve until we reach the point where the operating line and equilibrium curve intersect at a point, which is a pinch point. And in this case, what we have here, it's not the minimum liquid, it's the minimum vapor flow rate, because the vapor is the stream that I'm using to control or achieve what I want from the column. And as I mentioned before, we can use 25% more, 50% more than the minimum, so we can get reasonable flow rate with reasonable number of stages. So this is almost everything for absorption and stripping. I hope it made the topic clear, and I'll see you in the next video, inshallah. Goodbye.